Dr. Robert Zubrin is the founder of the Mars Society, and he is the creator with other people of the Mars simulation habitats in the Arctic and also in Utah, which many people have participated in over the years. So let him go right ahead with this talk. Go ahead.
All right. And I have the hour?
What?
Yeah.
You have, I think, 40 minutes because the students started at, I think, 50 or something.
All right, okay, so. All right, thank you very much, John, and thanks to all of you for coming to hear what I have to say. And I'm not going to be able to say everything I need to say, but fortunately I've just published a new book, and I've got copies of them here, and you buy them, I'll sign them, and I've discounted them. They're $25 ordinarily, be $20 here, either cash, or I'll take PayPal to Zubrin@AOL.com, but you'll have to. All right, so now you've seen the book. There you go. All right, so the topic of my talk is Mars Direct 2.2, how to send humans to Mars using Starship. Okay, because, people ask me all the time, you first proposed Mars Direct in 1990, it's now 29 years later, what's changed? Well, on the NASA side, the only thing that's actually changed is they've made a lot of discoveries about Mars with the robotic program. The robotic exploration program has been quite productive, and they have, in particular, discovered large reserves of ice on Mars. They, in fact, have discovered glaciers on Mars as far south as 38 degrees north, which is the same latitude as San Francisco, or where you are right now. And these glaciers at mid-latitudes contain more ice, more water than the entire Great Lakes of North America. So this is not a small resource. So as far as that is concerned, great, okay? But on the other side, on the actual mission technology side, the main thing that has changed is the prospect of using the Starship. Okay, so I will spend a few words on the current NASA plan to send humans to Mars, which is not a plan. Okay, that is, they propose to build a giant electric propulsion spaceship and base it at the Lunar Orbit Gateway and build another gateway in orbit around Mars, as you heard this morning, if you heard Administrator Bridenstine, and sail back and forth, and this puts Mars in the never never. We do not need giant electric propulsion spaceships to go to Mars. We do not need Mars orbiting space stations, and we don't need lunar orbiting space stations to go to Mars. And no one who's actually thinking about really wanting to go to Mars talks about doing these sorts of things. And in fact, the absurdity of the NASA plan of basing this electric propulsion spaceship at the Gateway is it would take 300 days by their calculations to get from the Gateway to Mars using electric propulsion. We can do it 180 days right now out of low Earth orbit with chemical propulsion. Okay? Nor does the electric propulsion out of the Gateway save you any mass, because the electric propulsion delta V from the Gateway to Mars is 7 kilometers a second, whereas if you were at the Gateway and you're using chemical propulsion, it's 700 meters a second, 1/10 as much. So even though the electric propulsion has 10 times the exhaust velocity, it also has 10 times the delta V. And so the rocket equation works out the same. It's the same mass ratio, but it's more mass because you've got a bigger dry mass carrying 500 kilowatts of electric propulsion to Mars and back instead of the 10 kilowatts a chemical spaceship needs for its life support. So this is not how to go to Mars. Now, what we do need to go to Mars is heavy lift. We've had heavy lift in the past. Okay, this is 1970. We are about to have heavy lift, SLS, although unfortunately the money that could have given the SLS a proper upper stage so it could actually do something is being spent on the Gateway. And then, of course, even more attractive, than the SLS for heavy lift is the Starship itself. Okay, now Mars Direct, you should know, I was on the team that did the preliminary design for SLS in 1988. That was 31 years ago. And now by comparison, you should understand, they cut the contract for the Saturn V in 1962. It flew in 67. That's 5 years, not 31 years. And we were inventing it as we went along. There was nothing new. And it had a capacity of 140 tons to low Earth orbit instead of 75. Okay, so, all right. But nevertheless, the SLS, or Ares as we called it at that time, was designed for Mars Direct. And it was designed with a proper upper stage that could throw 40 tons on trans-Mars injection, okay, which is the capacity you need to do Mars Direct. Now, if you do that, and by the way, when we designed SLS, we didn't design it with the thought that this was the best possible booster or anything of the sort. We designed it with the idea that it was the easiest booster to develop because it was just the shuttle stack without the orbiter. What could be more straightforward? We can have this flying by 1994, and if indeed, had we gotten it flying by 1994 or anything like that, it would have had a nice quarter century of service to speak for it, and doing all sorts of amazing things over the past 25 years, and be ready to be retired as something like the Starship came along. Okay? Unfortunately, right now it's a kind of a race to see which one flies first. But be that as it may, let's just talk about the capacity of being able to throw 40 tons on trans-Mars injection, which a properly designed SLS could do, which a Saturn V could do, and which a Starship would enable you to do as well. Okay, you do a Mars mission like this. In the first year of operations, you lift, you've got 120 tons or more of lift capability to LEO, which means 40 tons on trans-Mars injection. And you throw an unmanned Earth return vehicle to Mars. Okay, it reaches Mars 8 months later on a minimum energy trajectory. You land something like this on Mars. This is a two-stage Earth return vehicle shown here. One could also, in fact, do it in one stage. Saves a little bit of propellant to do 2 stages. Now we're making our return propellant on Mars, so it's not the mass of the propellant that matters here, it's the power required to produce the propellant. With 2 stages, with the Earth return vehicle as we designed it, it needed 96 tons of propellant. And since we didn't know about water on Mars at that time, we brought 6 tons of liquid hydrogen with us to Mars to react with Martian CO2 to make actually 108 tons of methane oxygen bipropellant on the surface of Mars. The Earth return vehicle actually only needed 96. We made 12 extra tons to power ground vehicles, okay, which would give the crew great mobility on the surface of Mars, which is what you need if you're going to do effective exploration. So the chemistry for this, we laid out. It's very straightforward. Hydrogen and CO2 can be reacted with a catalyst to produce methane and water. Methane is terrific rocket fuel. It's got the second highest exhaust velocity of any realistic chemical propellant after hydrogen oxygen, but it's much more storable and compact than hydrogen. And so your tanks weigh less and so forth. So it's right up there, and we can very easily make it. And the methane is much more storable than the hydrogen. So as the hydrogen boils off on Mars, we're just turning it into methane. We don't have to try to store liquid hydrogen on the surface of Mars. And then the water is electrolyzed into hydrogen and oxygen. The oxygen is your oxidizer. It stores at the same temperature as methane. Tanks can be in direct thermal contact. The hydrogen is recycled to make more methane. And then if you need more oxygen, you can make it by splitting CO2. Okay, if you can find water on Mars, then you don't need to bring the hydrogen, and you also don't need to do the third reaction, because if you're bringing hydrogen, you need some extra oxygen to burn it. if you're getting the hydrogen from water, then reaction 3 is out. Okay, and we've built machines that do this chemistry. This is actually the first one built in 1993. It was built at a total, by Martin Marietta, by a team I led at Martin Marietta in 1993. We did this program at a cost of $47,000, which is the lowest cost any program has ever been done at Martin Marietta. Okay, generally speaking, they cannot generate 3 charts for $47,000. And it worked, and it was 94% efficient when we turned it on the first time, and after that, it just got better. This works, okay? This is 19th century industrial chemistry. This is something that could have been done in Jules Verne's time. There are people at NASA, since their background comes from flight systems, they think making propellant on the surface of another planet is a magic trick. It's actually a lower level of technology than almost anything else done in a Mars mission, such as reaching Earth orbit. Okay, is much harder than doing this, let alone navigation across interplanetary space, entry and landing on Mars, and all the rest of the tricks that need to be done. Okay, so you make your propellant. Then at the next launch window, we launch 2 more payloads to Mars, another Earth return vehicle, and a habitation module. Our habitation module was a simple tuna can structure. Upper deck was living quarters, lower deck was the cargo hold and workshop kind of place. This is how we laid out the upper deck of the HAB. Actually, nowadays, the thing at the circular object at the center is the solar flare storm shelter. Nowadays, I would put it on the lower deck, but it doesn't matter. This is possible. Crew of 4, various areas, solar flare storm shelter. You shield yourself from solar flares using your provisions, water, food, wastes, all are excellent shielding material against solar flares. And we have enough of that on board the ship to shield a small area against solar flare. Solar flare happens, alarm bell rings, you go in there for 4 hours, the all clear rings, you come out. That's how you're safe against solar flares. The other thing that people mention all the time for Mars missions as a showstopper is radiation from cosmic rays, which you cannot shield against, but the magnitude of that dose is not that large. It's around 50 rem, half a sievert, for every year you're in interplanetary space, which will be, 6 months out. So if you go with chemical propulsion, you can get to Mars in 6 months, not 300 days. And this dose has already been taken by over a dozen astronauts and cosmonauts, and we've seen no radiological casualties among this group, nor would we expect there to be any, because based on the most conservative interpretation of radiation health physics, which is known as the linear no threshold hypothesis, which says that a small dose gives you its fraction of the risk you would get from a large dose, which is not what is ordinarily seen in toxicality. In other words, you can drink a martini a night for a year and experience no ill health. If you take 365 martinis in one night, you are dead. Okay, okay, but nevertheless, this is the conservative hypothesis. If you assume that this radiation dose represents about a 1% risk of getting a cancer at some point later in your life, assuming no advance in medical technique, that compares to a 20% additional risk you would get from smoking. Okay, it's actually quite comparable to the increased risk of living in Houston due to the petrochemical fumes that are in the atmosphere there. So, in fact, if we sent astronauts to Mars, and they live in Houston, you know, okay, it would actually improve their health. Now, Now, the other health effect that we really do see in space, not radiation, is zero gravity health effects, okay, which NASA has no intent of doing anything about, okay, and intends to subject more people to at the Gateway, as well as on their slow boat to Mars. But these do decondition muscle and bone, and something should be done about it. And the way to do something about it is artificial gravity. If you tether off the upper stage that threw you to Mars, you can spin this thing up. You can create Mars gravity in the HAB. And by the way, one use that I can actually think of for Orion, where Orion is inferior to Dragon for lunar missions because it weighs almost 3 times as much. And that's why even SLS cannot deliver it into low lunar orbit with enough fuel for it to come home. Okay, it weighs 26 tons. Dragon weighs 10. Okay, Apollo capsule weighed 9. Okay, but Dragon is half again bigger than the Apollo capsule. If you just used Dragon for this instead of Orion, you wouldn't need the Gateway at all. But which is why they're not using it now. But putting that aside, a good use for Orion is to send it to Earth orbit and tether off the upper stage that delivered it and spin it up and use it as a temporary but medium duration artificial gravity space station in Earth orbit. There, its larger mass does not hurt you very much, and its larger capacity, it is twice as big as Orion, would make it something you could live in for a month and learn about artificial gravity, learn about Mars gravity, learn about lunar gravity for medium durations of this kind. That would be a good use for Orion. But anyway, that's how I would go to Mars, so the crew gets to Mars in prime shape. Okay, then when they get close to Mars, you fire a pyro, you cut the cable, you go and land at landing site number 1 where the fully fueled Earth return vehicle waits for you. The other Earth return vehicle goes and opens up the next landing site where it starts making propellant, which make it the target for the next human mission, which flies there along with another Earth return vehicle, but which otherwise opens up landing site number 3, and so forth, so that every 2 years you launch 2 boosters, one to open up the new site, one to exploit the previous open site. 2 boosters every 2 years is an average of 1 per year. When we were launching shuttles in a serious way, we averaged 6 a year. So you're talking about 1/6 of your heavy lift capability to support human exploration of Mars. Means you can do the moon at the same time, you can do asteroids, you're not tying up your whole capability on Mars. So here is a view of the Mars base, the Earth return vehicle, the conical vehicle on the right. The lands first, the reactor that provided the power, it needed about 100 kilowatts to make the propellant. And then the tuna can habitat landed on Mars. The end of the mission, you get in the Earth return vehicle, you return to Earth in it. You leave the habitat behind on Mars. Each time you do this, you add another habitat to Mars, either as a network of small bases, or you could start landing them all in the same place and build up a major base, okay? Any way you want to do it. And this provides a base for exploration off Mars, to search for fossils of past life on Mars, because Mars was once a warm and wet planet, if the theory is correct, that life emerges wherever chemistry is permissible. Life's everywhere. We can find this out by going to Mars. If we drill, we might find extant life, because there's liquid water underground on Mars. The ancient Martian life forms, when they lost the surface, could have retreated into the groundwater. They could still be there. This is why we need to send humans to Mars just from the scientific point of view. Of course, there's other reasons that go beyond science to do this. And as I say, we could land a whole bunch of them in the same place to build a Mars base. We could use the same hardware to build a lunar base. And I think that after we prove the technology on Mars, we might want to set up a moon base too. Okay. And so here's the hardware set. And by the way, there you see it. This chart was drawn in 1990. Look at the vehicle on the left. Okay. That is the Ares, or what is now called the SLS, except it has a better upper stage, so it could actually do something. Now we have, though, something else happening, and this is what really my book is about, is we have an entrepreneurial space revolution. How can we take advantage of these new capabilities and this new dynamic to achieve the Mars and the moon and the asteroids and the stars, okay? And I'm going to focus here on Mars, but okay, now the first thing that came to mind when Musk started really moving was, okay, how can we use Falcon Heavy to do Mars missions? Okay, this is before Starship appears on the horizon. And yes, Falcon Heavy can do 60 tons to LEO. It's about half the capability of a Saturn V class launch vehicle. It's 3 times the capability of the shuttle or Titan IV or Ariane or Proton. So yes, it is something. It is the most powerful vehicle currently flying. It's not the most powerful vehicle that has ever flown. And with a 3-launch architecture and a crew of 2, you could do Mars missions that way. Okay, but now they've introduced, or not introduced yet, but Now, by the way, they talk about refueling the Starship on orbit. Now, if you can refuel something on orbit, it means basically that the same payload you can get to orbit, you can send to Mars. So if you're not refueling on orbit, the payload you can deliver to Mars is 1/3 of what you can deliver to orbit. Okay, if you are refueling on orbit, then the payload you can deliver to Mars is the same payload you can deliver to Mars. Actually, if you could refuel a Falcon Heavy on orbit, now you can throw 60 tons on trans-Mars injection. You do have a capability then, which is slightly better than a Saturn V. So that's a thought that you could do the whole Mars direct mission with Falcon Heavies if you could refuel them on orbit. And it's worth thinking about developing that capability, unless, of course, you're developing a heavier vehicle, which they are, which is, of course, the Starship. Now, this is a SpaceX chart, and here you can see their concept, which is they've got this large vehicle. Initially, it was something called the Interplanetary Transportation System, and it actually had a 500-ton to LEO capability, and they were going to fly this thing to orbit. Then they would refuel it with a whole bunch of other ITSs, and then they would send it off to Mars, and it could land with 500 tons of payload, and then they would refuel it and fly it home. Now, the initial concept here is presented by Elon Musk at the conference in Guadalajara in 2016, which is where it had its debut, was that they would have 1,000 of these, and each one of them would have 100 passengers, and they would fly them to Mars, and so you'd have 100,000 people delivered to Mars, each mission opportunity, which would therefore be 1 million people delivered to Mars after 10 opportunities, and thus you would colonize Mars, kind of like the Normandy landing here. Okay, now I wrote a critique of this, a rather extended critique, which was published in a journal called The New Atlantis, and you can read it online. It's still there. But I pointed out, number one, this thing was much too big. Number two, sending it all the way to Mars and back put one of these things out of action for 4 years, because it would take 2.5 years to do the round trip, and the next mission opportunity wouldn't occur for another 1.5 years. So it's 4 years out of action. You're sending 100 people to Mars with it. Who's coming back if you're doing colonization? Maybe a few deserters, criminals, retrogrades. Okay, but there's other ways to get rid of them. Okay, and in any case, it was, I mean, if you had someone with a legitimate reason to go to Earth, which I can't think of, but anyway, it would take like almost 2 megawatts of power over a 1.5-year period to produce enough propellant to send the ITS back from Mars to Earth, and that's an enormous burden to put on the Mars base. Anyway, I wrote this critique, and then a year later he came out with a revision, which was called the BFR at that time, and that was scaled down by a factor of 3. So it went from a 500-ton to LEO vehicle to a 150-ton to LEO vehicle, which is where it still is, although they have recently changed the name to BFR to Starship. Okay, so that's what I'm talking about. So when I say Mars direct with Starships, I am not talking about Enterprise. I am talking about this. But how could you do it? In other words, there's really 3 options. Okay, the SpaceX baseline, which remains fly it to orbit, refuel it on orbit, fly it all the way to Mars, refuel it there, and fly it home. Now we're talking about a 150-ton vehicle instead of 500, so the power requirement is down, but still this is a rather sizable vehicle. Okay, second option, I call it Plan TLI. Fly it to orbit, refuel it on orbit, but then only fly the Starship to an orbit comparable to translunar injection, which is to say a highly elliptical orbit around the Earth, but still bound to the Earth. It's an orbit just short of Earth escape. Okay, that's what translunar. That's what I mean. In other words, we're not actually going to the moon, but it's more or less it's the same delta V as required to do an orbit that would take you to the moon. Okay. Now, obviously, if you did this, you could also deliver payloads to TLI for the purpose of going to the moon as well, and we'll get into that. But anyway, the idea is then you're staging off of it. Now, the delta V to go to TLI from LEO is about 3.1 kilometers a second, 3.2. The delta V to go on minimum energy trans-Mars injection from LEO is 3.8, so you're talking about an extra 0.6 kilometers a second staging off of a vehicle like this, and kabing, you're on your way to Mars. That'll get you to Mars in 8 months. If you make it an extra 1 kilometer a second, that is a total of 4.2, you're on the 6-month orbit to Mars, and which is a very nice orbit for going to Mars, because that orbit, if you decide not to go to Mars, will loop around and come back and reach the Earth again exactly 2 years after you left, which is very convenient because the Earth will have moved around the orbit exactly twice and be there to meet you. If you try to go to Mars faster than that, you'll loop out further and come back and you'll miss the Earth. Okay, if you try to go to Mars slower than that, you'll loop back sooner and miss the Earth. That's why the 6-month trip to Mars is the right trip. Even if you had a better propulsion system like nuclear thermal, which is not planned for Starship, you would still want to take the 6-month orbit to Mars and take advantage of superior propulsion to increase your payload rather than reduce the trip time. But anyway, so we're staging off of this at TLI. Now, the Starship now loops back to Earth. It gets back to Earth orbit 6 days after it left Earth orbit, not 2.5 years. So now you could refuel it again and use it again and again and again, okay? So depending upon how fast you can refuel it, you might be able to use it every 10 days instead of every 700 days, okay? 1,400 days. It was 4 years. Then finally, there's the option of simply using the Starship as a fully reusable Earth-to-orbit heavy-lift vehicle and stage off of it out of LEO. Okay, that's pretty clear. You've got to, now at this point, now you have 150 tons to LEO, you've got your 40 tons on trans-Mars injection, and you just land it again, and this does not require any on-orbit refueling. So you do the math on this, and this is what you get, and I've been using for this analysis SpaceX numbers, which assumes that the dry mass of the Starship is only 85 tons. Now that is what Elon Musk calls an aspirational number. Okay. That is to say, they might not quite get there. That's a very light number, particularly since the Starship, as it originally was conceived, was made of advanced carbon things, and now they're just going to make it out of steel. So they're retreating from the certain ideas of very advanced materials to materials that are in general use, which means it's going to be heavier. But I stuck with the 85 tons, okay? And the heavier the Starship is, the less advantageous it is to send it further, okay? The lighter it is, the more credible that is, but here I've chosen the light number. Okay, if we use the Mars plan all the way to Mars and back, it would take 4 tankers to refuel it on orbit to send it on its way. If we use the TLI plan, it's 2 tankers. And of course, if we use the LEO plan, there's no tankers. Okay. The cargo delivered per flight. So you can see, of course, it has the biggest cargo delivered per flight with the all-up plan, 150 tons, versus 80 tons staging off of it TLI, and 23 tons. That's the actual delivered cargo to the surface. For instance, the LEO plan is sending something like 40 tons on trans-Mars injection, but of that, your payload is the 23. I know. Excuse me. The TLI plan and the Mars and the LEO plan, these, I preserve the spirit of the SpaceX baseline in that I assume a fully reusable Earth return vehicle, except it doesn't need to be so big. We're not sending the Starship all the way to Mars. And what I propose is something I call the mini Starship, which is actually something that Musk himself toyed with for another reason, which is a Starship scaled to be the upper stage of a Falcon 9. So if you can put a Starship on top of a Falcon 9, it's a small Starship, Falcon 9 can deliver 22 tons to LEO. So that's the payload that's delivered to LEO in addition to the upper stage of the Falcon 9. If we conceive of that as a ship, okay, that's the ship I want to send back from Mars to Earth. Okay, so instead of this very large Starship, well, only 85 tons actually, I assume a 20-ton mini Starship going to Mars, which is why this is only 23 tons of payload that is left on Mars along with a 20-ton mini Starship for the Earth return. Okay, so that's why you see return ship mass in next line, 85 tons for the all-up plan, 20 and 20 for the other two plans. Now here's a very important thing. How much power do we need? Because the Starship is 4 times the mass of the mini Starship, it needs 4 times as much power to produce enough propellant to send it home. So now it's 340 kilowatts instead of 80. That's important. That's, I don't know, like 4 football fields of solar panels instead of 1. Now this is another point. If we were talking about doing this as a NASA mission, it at least would be conceivable to talk about a nuclear power source on the surface of Mars. That is, if we had a well-organized NASA Mars program, as for instance we propose in Mars Direct, a nuke development should be part of that program. And nuclear power is the best kind of power to use on Mars. It's not affected by dust storms or this sort of thing. But if we're talking about going to Mars as a largely private initiative, you're not going to have a nuke. It's just not happening, okay? You're not going to get your hands on highly enriched uranium-235 or plutonium. You're going to have to use solar energy, okay? Now, and that means that the amount of power means you're paying in mass and size for power, okay? Mars, you can get solar energy on Mars, but it's only 40% as powerful as on Earth, and you have to over-design to deal with the contingency of dust storms and so forth. Okay, so you're paying a lot for power, and 340 kilowatts of power from solar energy on the surface of Mars is a formidable requirement. It would be very useful to cut that down to something more like 80. Even that's formidable, but obviously less formidable. Now, what about the amount of cargo delivered per Starship launch? The all-up plan does deliver more cargo, but it requires 5 launches per mission, because the 4 tankers plus the Starship itself. Okay, so the 150 tons divided by 5, well, that's 30 tons. The TLI plan, 26 tons per flight. The all-up plan, the LEO plan, 23. So in terms of the amount of cargo delivered per flight, they're quite comparable. Okay. Now what about the time between uses? I gave the Starship 1,000 days, even though it's 4 years between when it can go to Mars. If it comes back in 2.5 years, there's another 1.5 years where it could do something else, like support lunar missions. When it comes, so it's 1,000 days that it's actually out of action. Okay, it's more like 1,500 days when it's out of action vis-a-vis Mars, but 1,000 days where it's out of action for any purpose. Okay, the TLI plan, 10 days. 6 days to come back and land, and another 4 days to get it ready. And the LEO plan, I gave it 5 days. It actually could land the same day, but it'll take some days to get it going. So what do we have here? The use of the TLI or LEO plan cuts the power by a factor of 4. Okay, they cut the reuse time by a factor of 100. That matters, okay? The use of the TLI or LEO plan allows the Starship to be used to support lunar missions, among others, during the 2 years in between Mars flight opportunities, okay? And this is, by the way, a very important thing, and this is, by the way, one of my principal objections to the current lunar architecture. okay, they're not assuming Starship, they're assuming SLS. That's fine. Let's say SLS is the best you've got. Do you really want to tie it up supporting lunar missions forever? No, the Moon Direct architecture, which I'll talk about on Sunday and which you may have heard about, we do use our heaviest lift capability in the initial phases of the program, okay, to establish the base on the moon. But once ISRU is operational, we can continue lunar missions with a medium lift launch vehicle, and namely a Falcon 9 per mission, freeing up SLS to support Mars. In other words, the way a lunar architecture that supports Mars the best is the lunar architecture that demands the least launch capability for itself. Okay? It's like Normandy Beach. You send your crack divisions to take the beach, but once the beach is taken, it can be run by rear echelon forces, and the crack divisions can go off to liberate the rest of France. Okay? So that's how you should think about a lunar architecture. Okay, to the extent it needs SLS, you want it to need it the least, and clearly only in the initial phases before you have ISRU. After that, if that's the best you have, send it off to do the harder stuff. Okay, now there's two different things. The TLI and the LEO architectures require the development of a mini Starship. The SpaceX baseline does not. Okay, that's its principal virtue, that it is done with only one system, the Starship. Although it does require development of the tanker version of the Starship, as does the TLI system. The LEO version does not. It requires no on-orbit refueling at all. Okay, but the mini Starship is a very useful thing. It would turn Falcon 9 into a fully reusable medium-lift launch vehicle, which would have tremendous commercial utility. Okay? It also is the best way for Starship to support lunar missions. Once again, landing this whole gigantic Starship on the moon and having to refuel it there puts a great burden on a lunar base in terms of propellant making to support the mission. And are you really sending hundreds of people back from the moon to Earth all the time? Whereas the mini Starship would be an excellent lunar return vehicle and impose much less power and propellant making requirements on the lunar base. And finally, the mini Starship could be used to do Mars missions now, because you could refuel a mini Starship on orbit with a single launch of a Falcon Heavy. So you already have the lower stage of the mini Starship. You already have the Falcon Heavy to be its tanker. And there it is. So that's my argument for that. And we'll see what happens, okay? You know, Musk is very hard to convince when he gets his mind on something, but he is convincible. And as facts emerge, okay, this is why he's been successful. He sticks to his guns, but he's able to switch his guns when the truth emerges. He does not stick with an idea once it's shown to not be the right one. So I think this is the shape of things to come. Here you have a Mars colony, and yes, the initial colony will be habitats delivered to Mars. And by the way, once you do have a Mars colony, what's the cheapest way to get to Mars if you want to immigrate? Ride the freight. Ride the freight. If we're sending habitat modules to Mars filled with supplies, and you want to immigrate to Mars on the cheap, say, can I ride it along with the freight? Yeah, so forth. Okay, you're responsible for your own food. Leave only footprints behind, and so on. Okay, but then, of course, eventually building structures on Mars, including domes, underground vaults. Bruce Mackenzie is here. Long ago proposed building underground vaults on Mars. It's an excellent idea. The domes for the surface and greenhouses, and underground vaults for much more extensive habitation. So I think we can do it. And I think they will do it. I mean, the one thing that has happened here, what Musk has done and is doing goes well beyond the fact that he's introduced a number of very attractive systems, Falcons, Falcon Heavies, Dragons, and so forth. He has proven a point that it is possible for a small team entrepreneurial team that is well led, decisively led, to achieve things that previously was thought that only the governments of major powers could do, and not only that, achieve them in half the time or less, and certainly 1/10 the budget or less. And this has set off an entrepreneurial space race, and not only from other billionaires with discretionary money thrown around, but even working engineers. You know, Cantrell, I think, was here yesterday. His vector space. This guy has no more resources than I do, which, you know, is but he's got investors, and so does Rocket Lab and Firefly. And Rocket Lab is even from a country that it doesn't even have a space program, so this has opened it up to people from any country. But of course, at this point, leading the charge is SpaceX, and I think that if they don't trip, okay, they will have humans on Mars before the next decade is out. Because I think that if Starship is flying by, say, 2024, the next president, okay, will, when they come into office, will look at the situation. Can I have humans on Mars by the end of my second term? Absolutely. Can I have them in my first term? Possibly. Well, then let's do this. So I'll be happy to take some questions. By the way, I also want to remind everyone the Mars Society is having its conference October 17th through 20th at University of Southern California. There's an open call for papers on our website, marssociety.org. You can speak there, submit a 300-word abstract, or just come and enjoy the conference. So, questions? Bruce?
You asked what's the cheapest way to get to Mars? Is it to ride the freight? I maintain it would be born there.
Point taken. He said, "What I say the cheapest way is to ride the freight." He said the cheapest way is to be born there. Okay, and he's right. And that's why Mars needs children. Okay, and that's why Mars needs women. And the okay, and so well, I'm not going to badmouth Orion. Artemis, she killed Orion, you know, but the, anyway, sir.
What's going to happen to kids who grow up in 1/6/13?
We don't know. Okay, we don't know. And of course, this is a fundamental question. It's even a more severe question regarding lunar settlement, which has got 1/6G. This is one reason why I think we need to start studying artificial gravity, which also gives us the option to study partial gravity. And once again, I think this would be a very good use for Orion as temporary artificial gravity space stations. We could fly in Earth orbit. We could start learning about questions like this, both with human crews and also other mammals. In the back, sir. Well, I'll leave the design decisions on that to SpaceX. They seem to be pretty good at it. That is an idea that's been around for quite a while, and we'll see how it turns out. But I certainly don't criticize SpaceX's ability to do math.
You probably just had one or two more questions because we're
All right, one question, and then you got to buy the book. Okay. One more, over here.
Robert, you have well, I'm sure you have an opinion on the Buzz Aldrin idea for Mars cycler?
Cyclers are certainly possible. I think they are a downstream development. We built the Transcontinental Railroad after we settled San Francisco. Okay. That is, first went, trappers and explorers, and then went pioneers and wagon trains, and then when there were enough people there to justify a railroad, we built that too. So there'll be cyclers someday, but I don't see that as the way we do initial missions to Mars. I guess that's it. Thank you very much.